joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Hello everyone, and thank you for joining us today, and welcome to today's webinar from our Standards Activities Board series. In today's presentation, the next data rates of Ethernet with John D'Ambrosia. My name is Scott Levine, and I am the membership manager here at the IEEE Computer Society. Before we get started, I'd like to address some housekeeping items. This webinar is being recorded. You can ask any questions in the Q&A box you see on your screen. John will answer as many questions as he can following his presentation. And if possible, please reference the slide your question refers to. And a copy of the slides and the recording will be emailed to you tomorrow. The IEEE 802.3 Ethernet Working Group has put forward various efforts to address the need for a higher Ethernet rate. 802.3 is just one of the many standards founded by IEEE that you can learn more about. Keep up with your ongoing calls for participation and get involved with our standard board activities. The IEEE Computer Society is a global community where you can learn about the standards and discover more. As part of this network, you have the opportunity to connect with professionals from all over the world. You can expand your knowledge with the Computer Society Digital Library, which features over 40,000 papers and articles highlighting the latest in networking technology research. Furthermore, you can grow with other professionals through various events such as technical communities, conferences, and chapters. Information will be shared with you after the webinar, and you can always learn more at computer.org. The IEEE 802.3 Ethernet Working Group monitors and periodically performs assessments of the industry's bandwidth needs. Over the past 15 years, 802.3 has undertaken efforts to understand industry's bandwidth needs in order to assess the need for higher Ethernet rates. The last Ethernet bandwidth assessment published in April 2020 indicated the need for Ethernet communities to start considering Ethernet rates beyond 400 gigabits per second. Today, John will review the trends noted in 802.3's latest assessment and will review efforts underway to target 800 gigabit and 1.6 terabits per second. John D'Ambrosia is a distinguished engineer at FutureWay Technologies, a U.S. subsidiary of Huawei. John is the chair of IEEE 802.3df 200, 400, 800 gigabits per second and 1.6 terabits per second task force. Previously, he led the task force that developed the 4100, 200, and 400 gigabit per second Ethernet, as well as the new Ethernet applications ad hoc. John is also a member of the 802 Executive Committee and is a senior member of IEEE. In addition to his multiple roles in 802, he was an advisor to the European Photonics Industry Consortium from 2019 to 2002. He was the chairman of the Ethernet Alliance from 2011 to 2019. His previous work experience includes Dell, Force 10 Networks, and Tyco Electronics. John, thank you for being here today, and the floor is yours.
Thank you very much, Scott. Good morning, good afternoon, good evening to wherever you are in the world today. Thank you for joining to hear about what is going on with the next data rates of Ethernet. I'm not going to repeat this. Scott did a wonderful job reading that. Before I do get started, I do need to put the classic foreword on regarding that anything I say today is my opinion, and I am not speaking on behalf of IEEE. All right, so for today's presentation, I'm going to do a brief introduction, and then I'm going to talk about the bandwidth assessment. Then we will go into the DF project, the progress, and then we'll have some closing thoughts, and then we'll have time for Q&A. So let's get started. So I think a good place to start, first of all, is Ethernet and the different rates. You know, we talk about Ethernet and all of these different rates that are out there. There are different rates for Ethernet because there are different applications for Ethernet. This chart, which I borrowed from the chair of 802.3, kind of highlights all of the different things. Now, many of us are familiar with Ethernet and its emergence in the enterprise application space. But since then, Ethernet has grown into many different application spaces, the data centers, access networks, to the latest automotive and industrial. And another one that it's not really an application space per se, but power over Ethernet. So basically, when you use those category 5 cables, you're actually able to power things, and actually even single pair over Ethernet. So when we provide a copper connection, we provide power. This is found home in supporting many, many different applications in the automotive and enterprise, as well as in security and other places. So you can see that Ethernet is going in all sorts of places. In addition, there are rates of Ethernet that are used, and we continue to go really fast. But in some cases, it's not really appropriate. Speed is actually relevant to the application that you intend to use it for. So, for example, industrial, which is more in the 10 meg, 100 meg space, 400 gig would be overkill for that, right? So not only overkill, but it would also be a cost issue. Ethernet covers all of these different applications and different speeds and different media with different solutions. Today's webinar is going to focus in on Ethernet's growth beyond 400 gigabit per second, and specifically 800 and 1.6, but we'll get to that in a second. Now, as Scott noted, we have been doing bandwidth assessments for about 15 years now. And there's a reason for that. First of all, you get into a lot of discussion about, well, what does an application need? And if I go back to the first time where I really started to remember that we needed to understand bandwidth trends, it was in the project that was defining initially 100 gigabit per second Ethernet. That project, the 802.3 BA project, got to a point where the server community was saying, we don't want 100 gig for servers at this time. We won't be able to use it. We'll need 40 gig. And that was really the first time that, in my experience, where it was something more categorically than, oh, we need to go faster. Right? So we really started to look at the trends and understand the different needs between the computing space and the networking space. And when we completed that project, about a year or so later, we realized that we needed to keep on top of what was going on in the industry with bandwidth. So we started a new project, a new assessment, if you will, that was done we refer back to in 2012. And at that point, that was really the consensus that ultimately we were going to need something beyond 100 gig. Now here's a snapshot of the two pretty pictures. And it'll illustrate to you what's going on here. In the figure on the left, we show the two curves. And basically what we were recognizing here was that networking was growing faster than computing at the time, okay? And what we saw here was that networking was going to need 100 gig before computing did. And computing was going to need a 40 gig solution. And that really drove the project forward. At that point, the industry was not reaching consensus on what speed to choose. And ultimately, it was understanding that bandwidth trend that I'm showing here on the left that allowed the group to make progress. The figure on the right is from the 2012 bandwidth assessment. And based on that, we saw a large variation in bandwidth for the different applications. And what we actually saw was that we expected bandwidth requirements to grow for a given application space on average by a factor of 10 in 5 years. So this really led to us recognizing that we needed to start the next speed after 100 gig, and this is ultimately what led to the 400 gig project, which then included 200 gig. So you can see bandwidth has been very important. Understanding these bandwidth trends has been very important in the 802.3 community as we progress Ethernet to the next higher rate. So with that, let's get started then on the 2020 Ethernet bandwidth assessment. This was initiated after we had completed the 400 gig project about a year or so later. And once again, we recognized, okay, we better keep on top of this. That assessment focused really in on this basic equation. When you look at a bandwidth explosion, it really comes down to 3 factors: the number of users, the access methods and rates, and the services that are offered over them. And what we did was we looked at various sources of data targeting each of these, and we basically had to get to, well, what does that mean to the bandwidth? Okay. Now, I'm not going to give you the full report here. That would be an hour-and-a-half presentation on itself. I know, because I've done that already. But I will point you to the report and to the tutorial. Both of these are downloadable at the URLs that are provided. And you can get into much, much more detail, see the source data, see the actual report, and see the tutorial that we provided on it. That kind of gave an overview of all the material that we had, which we gathered over a 1-year process. But let's focus in on highlights from that at this point. Okay, so first, the increased number of users. Now, one of the interesting things here is that, remember, I'm giving you a summary of the 2020 assessment. So that assessment was performed gathering data throughout 2019, in some cases forecast. But you need to look at it as a snapshot at that point in time, okay? At that time, about 60% of the world population was internet users. That number, last I checked in 2020, was now at 62%. So we have roughly, in a short period of time, about 18 months, we saw half a billion new internet users. Now, mind you, this might not be a person. It could be something else, right? A lot of machine-to-machine language is going on nowadays, or machine-to-machine communications. But half a billion new internet users. Okay, now, when we look at the users, the consumers like ourselves, we also noticed that, okay, in 2017, there was roughly 2 devices per individual, and that was forecasted to grow to, I think it was 3.2 by 2022, this year. But with that said, what we saw was that the bandwidth that every person was using was growing much, much faster. And over that same period of time where you were seeing a 50% growth in the number of devices, you were seeing 190% growth in bandwidth, right? So all those super users out there, thank you. You're giving me job security with all of the data that you're using. And we are seeing a lot of that. Next then is the access methods. And I think this is a really important area. And you think about it, and the reality is that data is going on the internet all the time. And the more that we're on the internet as an individual, the more that we're using data, one way or the other. So think about it. There was a time where we were using data just at our computer. Then we got our phones. Then we got our smart TVs. Then we had unlimited access if you have that type of service. So you're probably streaming in your car now. All of that data continually adding up. So it's more people on more of the time using more data. You see more of a growth. And it's really mobility, and that mobile connectivity has been a big driver. It's really had the highest growth in that 5-year period that I was talking about. Video, I think, is no surprise, is really the dominant bandwidth driver. And as we go to higher resolution cameras and pictures, we use more bandwidth to communicate all of those. Now, I did comment before about the mobile machine-to-machine connections. And yeah, they are growing. There's a dominant number of connections, but they are not high bandwidth consumers. Maybe someday that'll change. You know, maybe if video starts going into more of those connections, we'll start to see more bandwidth grow there. But there are still a lot of internet connections where, or 10 meg, that's fine for the application space. Now, one of the other things that we did notice, and we noticed this both in terms of the mobile connectivity and global traffic, is that there is a big difference, a huge difference actually, between peak traffic and average traffic. In the case of the global traffic, we saw that there was a 6x difference. So peak traffic was 6 times the amount of average traffic. Got to keep that in mind, because that's what we have to build networks to support, the peak traffic, not the average traffic. So when you start getting into discussions about what people are seeing from a bandwidth perspective, make sure that you are clear with what the data that they're giving you, because there is a substantial difference between the two. Next up then is the services. And as I've already talked about, video is a killer app. And that gets worse as we start to shift to ultra high def. And I just bought a new TV myself, and I was looking at that, and now I have the choice of, do I buy a 4K TV, or do I look to the future and buy an 8K TV? It's coming, right? All of that will provide more bandwidth, or will require more bandwidth as well. There are other applications as well that are emerging. I think one of the big ones that we saw was virtual reality and augmented reality. And actually machine languages and machine learning is a huge one. For example, we saw there was a comparison made to computing has been doubling every 36 months. And now the required doubling for machine languages is, every 2 years, not 3 years. And the requirement for machine learning is that doubling every 3 months. So you also see machine learning and such having a big impact on bandwidth requirements as well. I am going to admit that these bandwidth assessments that we've done, they are contribution driven. So what other applications weren't covered? We don't know yet, and that's always the uncertainty of the future. I always anticipate that more applications will come that will require more bandwidth. So what does this mean from a bandwidth explosion perspective? Well, I always like to just simply say traffic growth is up and to the right. Plain and simple. I've yet to see any picture where it really is going down. The only place where you may see it go down is the growth rate. That doesn't mean data is going down. It just means it's not growing as fast. But it's still going up and to the right. There is a broad diversity of growth, and I'll show you some data in a second. It varies on a regional basis, on an application basis, on a time period basis, all over the place. And when we look at the data that we collected, we saw from an application basis that if we normalize that data back to 2017 traffic levels for those given applications, that the traffic for any given application might have grown anywhere from 2.3 times that traffic to 55.4 times that traffic. And that's what people are asking Ethernet to keep up with, right? Those are the bandwidth requirements that they need to support. And this problem only gets worse if we don't provide them with these new speeds of Ethernet. So, that's where it comes in. So let's look at this from a summary perspective. All right, so let me draw the chart here. Okay, sorry, user error there for a second. So this was the data that we had from 2017 to 2022, and there's a range of different applications. There is the peering networks, there's global IP data, IP video data, global CDN networks, mobile data, data center capacity shipped, mobile consumption subscriptions, virtual reality. Okay, and Why these traffic levels all look the same is simply because they're normalized back to their 2017 levels. That's the only way that we can do it. If I were to try to map all of this data and compare it to the data center capacity shipped, none of these lines really would probably show up when you look at what's happening with data center capacity and the shipments that are going there. It's that great. So we have all of this data, and we reported this. This report was published in 2020. We were really looking for a 5 years, a 5-year roadmap. So what we did was we just assumed that there would be a consistent CAGR for each of the different applications based on whatever that it was, and we just projected out from there. And this is where you see the 2.3 to 55.4 number that I was referring to. All of these growing at different growth rates. If you look at Ethernet, in 2017, we introduced the 400 gig speed. If we were to start a new project, and we're looking right now at the 24-25 time frame, if it was 800 gig, that represents only a 2x increase in traffic or in capacity, where 1.6 would still only require would only provide 4 times the capacity of what it was in 2017. So now, mind you, this is not completely relevant. We're looking at applications and individual nodes in the network, but we do want to make sure that we provide these solutions that are going to be bandwidth intensive, the Ethernet solutions that they need. All right. Okay, so let's start off then looking at the DF project. When one looks at Ethernet, as I talked about before, there's lots of different applications. And even when we say computing or networking, there's lots of different applications and Ethernet solutions that are provided. From the servers that go to a top-of-rack switch, to the leaf-spine switches, up to the routers, up into the data center interconnects, there are Ethernet solutions at all of these nodes. And they all service different applications. Okay, so when you're looking at these server connections, you see a lot of multi-mode fiber or twin-ax connections, and people look at that to service, probably in the 30 to 50 meter range. Now, I'm not saying twin-ax does 50 meters. I'm saying they have a choice of the two, and they need to cover, in general, that range. Then when you start to look at the top of rack to the leaf spine, well, now you're looking at 50 meters to about 500, and people are using multi-mode fiber, single-mode fiber, duplex parallel solutions. And, today's rates, they have 100, 200, and even 400. We need to grow beyond that. And I should have said in the servers, 100 is very common, but people are starting to introduce 200 and 400 as well. And then we start to look at the leaf spine router connections, which really tend to be more of a duplex fiber solution. And that's 500 meters to 40 kilometers. And then when you start to look at DCI, you're looking at 80 kilometers, and that's being done over a DWDM system, all right? Or they may be using the capacity or the capability of the solution to go over a single mode fiber for that length. So there's a lot of different things that that can be used in this higher speed Ethernet, a lot of different solutions that we have to worry about. And what's not even shown here as well is all of the electrical connections that are inside the boxes. This is just the connections from box to box, if you will. There's a lot of electrical interfaces from between different chips and the chip to modules that Ethernet provides specifications for as well. One of the other aspects going into this generation of higher speed Ethernet is the recognition that in many cases the ports that are on a lot of the equipment today are universal. They're multi-rate and they're multimedia. Okay, so they'll be using parallel solutions. So for example, if you were to imagine a parallel solution that's 8 lanes wide, and by lane I mean a differential pair, a fiber, a wavelength, people want to use the flexibility of that port. So a lot of times people don't even refer to the Ethernet rate of the port. They refer to the max capacity of the port. In this example, I have a port that has 1.6 terabit capacity. And what we typically find is that people like to use 1, 2, 4, and 8. They go binary, and they like to have those variations. So this by 8 module, these 8 lanes, you might use 1 lane for supporting a 200 gig solution. You might use a 2 lane at 200 gig for 400 gig Ethernet. You might even do a dual 800 gig port. So use 4 lanes for one port of 800 and 4 lanes for another port of 800. Or you might use all of it to have that 1.6 terabit fat pipe, right? The market is using this. It has become very, very popular. It was something that we introduced really during the 802.3 BA project with 10 gig and 40 gig. And it has progressed with each new signaling rate that we've introduced. So 1040, 25 100, 50 200, 100 400, 200 800. All right, and this is kind of a simple example to illustrate that. So you can look at all of the different signaling rates that are offered. So we have all of these different families of Ethernet. And then you can look at the width of the interface. So 1, 2, 4, 8, 16 lanes. And then you can look at the lane rate. And you know, this might be how fast an individual differential pair is going, or how fast an individual wavelength is running, or an individual polarization is running. And then you just multiply the two, and that's the product. So if you were to look at today, what you would see is that Ethernet has already developed 1, 2, and 4 lane solutions based on 100 gig signaling to support 100, 200, and 400 gig. During the course of defining the 800 gig, we soon realized that people are becoming much more comfortable with using 8-lane wide solutions. I won't say that's the typical sweet spot. That's usually been 1-lane and 4-lane solutions. You can think back to 1000 base T is 4 lanes, Zowie was 4 lanes. But what we're seeing now is that people have to deal with growing bandwidth demands, and they're willing to go further parallel than just 4 lanes and grow to 8 lanes. So 8 lanes of 100 will give us 800 gig. And the nice thing there is that we already have a lot of the basic technology developed for 100 gig. Now, I did say the sweet spot in general has been the 1 and 4 lanes. So there is an anticipation that you will see a 4-lane, 200 gigabit per second lane, 800 gig Ethernet solution. All right, so that's that main one that I'm showing there in the circle. But Ethernet is also a product, a family, if you will, that always looks backwards. And as we grow as we develop the 200 gig speed solutions, we don't want to strand those 8-wide solutions. So that's how we're going to get to 1.6. Really, it's supporting those legacy form factors of by 8 and their growing market adoption. Future 200 gig speed to be developed, 8 by 200, 1.6. Now, the other thing also to note is that this will be applicable to other speeds. So you can imagine 2 lanes of 200 gig to support 400 gig. This will give us a higher density 400 gig solution. Or even 8 lanes of 200 gig to give us a really high density solution. You can imagine that being used for your server interconnections, okay? This gives us a whole family, if you will, for this now 1 by 1 to by 8, the same one that I showed here previously with 100 gig. So while we're providing a higher speed solution, we're also providing an upgrade path for those people who used the 1 to 8 100 gig family as they grow to a 1 to 8 200 gigabit per second family. So as I said, Ethernet has a lot of different specifications that it provides. And this project has chosen a whole bunch of objectives. Kind of scary when you look at it, and I get that. This is definitely what we would call an eyesore chart. I think anybody can agree to that. But it's really not as scary as it looks. Why? Well, there's really basic groupings here that we can use. And remember, I talked about this 1, 2, 4, 8 lane approach. Okay, so first of all, there is the opportunity for us to reuse all of the 100 gig technology that has been developed in multiple projects in 802.3 to basically just change the number of lanes and come up with a new solution. So in the case of the electrical interfaces, or which are referred to as the OWIs, the backplane solutions, the copper cable solutions, multi-mode fiber, both 50 and 100 meters, single mode fiber for both 500 meters and 2 kilometers, we're able to reuse all of that 100 gig technology and provide a whole bunch of very quick solutions. In addition, you could do 16 by 100. Now, this is kind of a special case because this goes into a new speed, and we'll talk a little bit more about that later. But you can see it's not that bad when you start to divide things up. There's also a whole new group of things that's 200 gig per lane based, and our electrical interfaces and our copper cables. Okay, so really you're developing that basic building block and then just applying it to 1, 2, 4, and 8 lanes. We'll do the same thing optically. All right, so develop a 200 gig optical signal that can be used really just over the single mode fiber at this point for 502 kilometers. Most of this is parallel fiber with the exception of this 1/4 lambda solution, which is a WDM solution, a duplex fiber. And then we have this last one, which is for 10 kilometers and 40 kilometers. Now, traditionally, Ethernet has leveraged direct detect optics. With recent projects, 802.3CN and 802.3CT and CW, we introduced coherent solutions, both at 100 and 400 gig. The CW project, another one of my little side projects, is in full development at time. But you know, coherent is now going more mainstream and not just the typical operator type of applications. And it's very likely, well, I'm not going to say it's very likely at this point. At this point, 10 and 40 kilometers could use either of these two solutions. And that is going to be a debate that is underway in the task force. And we'll talk a little bit more about that as I discuss the progress. Okay, so that big eyesore chart that we looked at, it's really not that bad when you start to realize it's really development of a lot of basic technology, 200 gig electrical, 200 gig optical, reusing 100 gig development efforts, and one new area. And I'm not going to understate how challenging these new areas will be and the debates that are going to happen. But in the grand scheme of the project, it's not as frightening when we start to think about things in this manner. So our progress to date. Let's first of all talk to general architecture overview. Okay, so I'm going to use a couple terms here. I just want to define up front. So the physical layer is everything below the MAC all the way to the medium. So that includes the connector. When we talk about the PHY, we're talking about these 3 sublayers here, the PCS, the PMA, and the PMD. The PCS provides the coding. It may also provide the FEC. In the case of 800 and 1.6, it will provide FEC. The PMA does our muxing, demuxing, retiming, and then the PMD is actually what drives the medium. Okay. We refer to the MII, and that's a connection between the reconciliation sublayer and the PCS. This will become more important as we start to talk about the 100 and 200 gig signaling. And in this MII right here is really very important. Okay, so important that we have what's called an MII extender. And in this case, I've given an example of 800 gig. So you have, before we talked about the RS. Now the MII covers down through all of here. Now the application one could think of is, imagine you have a big chip on a host board and you're going to communicate with your optical module. You might cover all of that work, all of the PCB on the host board with this extender. Okay, and then you go back to the MII, re-encode, and then you can go into a PHY, which will then drive the medium of choice. All right. This is really a very flexible technique. It allows us to enable PHY choices because you can change the PCS/FEC as you need for a given PMD. We might be able to use this, for example, for a copper cable PHY. So you could basically get the reach using the extender, and then you could drive the cable length through potentially an active cable assembly, or maybe even you have a driver next to the cable. And this might allow you to get to further reaches. Now, there are some cons with the extender. You have to worry about power. You have to worry about the complexity. And then the big one in a lot of today's is latency. So actually, I should say the big two are power and latency. So there are some issues associated with it, and it's a balancing act that we have to deal with. Now, as we look at defining 800 gig and 1.6 terabit, I've talked a lot about 100 and 200 gig signaling, but the reality is that a lot of the debates are happening with the forward error correction schemes, okay? There are three basic approaches: end-to-end, segmented, and concatenated. And, right now we have a lot of people who are really saying one is better than the other. But what we need to understand is that Ethernet worries about multi-generation interoperability. So we've got to figure out a way for an 800 gig based on 8 by 100 to interoperate in the future with a solution that's based on 4 by 200. So we've got to worry about all of the issues that come along with that. We also need to worry about, well, what is the coding gain that is needed for each physical layer specification? Maybe we can find one that will cover most of them. Maybe we'll need a couple. Maybe we'll need more. And then, as I said already, we have to worry about the power and latency. And I'm going to say this this is one of the things that I always say as a chair in 802.3. It's our responsibility to develop an interoperability standard, not specify a single implementation. If we do our job right, we should enable as many implementations as possible. The more implementations we can enable, the better off we are. And that's how I always approach these projects. Okay, so the reality is that the architecture that we have developed and adopted is one that can support all three: end-to-end, segmented, and concatenated. This picture might give you a better idea of what I mean. So in the case of end-to-end, you have a single FEC. It's applied at the PCS, and it drives all the way down through the medium to the far end, and then the FEC is it's unfect, defect, before it goes into the receiver receive card MAC. In the case of a segmented FEC, that's kind of, I explained that already with the extender. You have an extender, that FEC is then terminated, you go back to the MII, and then the FEC that is specific to the PHY is brought in, and then at the far end, the PHY does the defecking, and then it goes into this extender again. And then in concatenated, and this one gets a little bit confusing, you have an outer FEC, which is combined then with an inner FEC, and it's the product of those two FECs is what provides the solution. There's a lot of different challenges to all of this, and we're trying to figure out all of these different things. We're trying to figure out what FEC codes we can and can't reuse. And we're also looking at all of the different physical layer specifications. But we have to remember that we're developing, I'll go back to, we're developing an interoperability standard. All right, so at this point, this shows the progress of the task force. So it may not be a big surprise to people on the call, because I said we've made a lot of progress, or we've developed a lot of work on 100 gig. And everything that we've adopted at this point is based on 100 gigabit per second per lane solution. All right, so you can see we've got a big chunk of stuff here. We didn't do the 1.6 AUI because that's going to be related to the total solution for 1.6 in the Mac. So we're holding off on nailing that one down. So I kind of just touched on this. So if I look at the progress, we're leveraging work from 802.3bs, CU, CK, and DB to apply to the various various interfaces noted here. The 200 gig per lane is going slower, right? And that's to be expected. It is a newer rate, and there's a lot of development effort that has to happen. What I can say in terms of decisions, we have made one real decision at this point, and that is that we will be using PAM4 optical modulation for 200 gigabit per second per lane for 500 meter and 2 kilometer single mode fiber reach objectives. We may have adopted the modulation, but we do not have any adopted baselines. And at this point, we have limited electrical channel data. So this would be all of the, the copper traces or copper cabling and the connectors, all of that. We have a limited amount of data. We're getting more each time. Another thing that may be of interest to people is that we have not received any official request or presentations talking about electrical interfaces for co-packaged or near packaged optics. So if there's anybody out there in computer society land that is concerned and wants to see the standard address these. I'll remind everybody that standards are contribution driven. Don't assume that we're just going to do something that you want. If you want to see something happen, please get involved and bring the data that we need to drive that development. At 10 kilometers and 40 kilometers, at this point, there are no adopted baselines. We did have a straw poll. That straw poll did show that there was strong support at 10 kilometers for the coherent solutions, though there's still a lot of people who are looking for more information. So it's going to be really interesting to see what happens with that 10-kilometer space. 40 kilometers is pretty well assumed, excuse me, by most parties that I've talked to be coherent. The real fight seems to be, and debate seems to be at the 10 kilometers. So let's revisit this spec debate again. As I said, the architecture can support all of them, and we do actually anticipate that more than one spec scheme will be used because of the different PMDs, and I can say that with a certain level of historical reference, because at 400 gig, we actually do have two spec schemes. We have the end-to-end, and we have the segmented already used. The segmented is one that we're using for coherent optics. Very clear that, you know, we can see that people are doing that, though some people are proposing concatenated for that in the future. So there's a lot of debate there. And once again, I'll bring up this multi-generation support. So remember, we have to worry about everything working together. So there's a lot of 100 gig electrical interfaces and 100 gig PMDs. That stuff is going to have to work in the future with the 200 gig electrical interfaces. And we're also going to have to worry about the 200 gig PMDs being able to be supported by the 100 gig stuff. So we're trying to figure out how to make all of this stuff work together. Now, I think the problem that we have, and I've had to point this out, is that people come into the project and they have a definite implementation that they want to see enabled. In the case here, what I'm showing, and I'll call it the ideal case, you're going to have a big chip talking to your module, going to the far end, and you have a module there, which also then just communicates to the big chip. And that's it, right? So we don't want to have all of this other stuff. Well, that's fine, but remember, I've already talked about 100 and 200 gig. The reality is, as I said, we write standards, not implementation specifications. This is a single implementation up top that I'm showing. If you look at the reality of what Ethernet has done in the past, we've always allowed two AUIs, two electrical interfaces on a line card. That would be a way simply to allow 100 gig solutions to interact with 200 gig solutions, or maybe 100 to 400 in the future, right? And we do that at both cards, right? So the simple example up here, that may be what somebody wants to implement, but this is the reality of what a standard has been addressing, an Ethernet standard has been addressing in past higher speeds. Okay, so let's talk a little bit about the concatenated, and I just showed you that ideal case where basically I have a line card and it's going across the electrical interface, in this case the 800 GAUI4 that talks to a module and goes across down here, the 800DR4, which is the PMD, and it goes back up. And wow, this looks great. It looks really simple. That's great. But it assumes that both ASICs and optics are based on this 800 GAU4 being present, this 4-lane solution present on the transmitter and the receiver. Simple reality is that that's not the only world out there. So we can make those assumptions that I'm going to develop a line card. It's going to be based on 4x200, both electrically and optically. And I'm going to want to communicate at the far end with an 800 gig card. But remember, in general, the electrical doesn't keep up with the optics, right? The optics leads the electrical. So I assume that there will be 800 gig solutions based on 8x100 out there, and out there before the 200 gig based optics are out there. So what happens now when I want to support this legacy card based on 8x100 with this 4x200 solution? Remember, I showed you that nice, pretty picture here. So this is, this not, well, shouldn't have done that with the animation, but you can see this nice, pretty picture. It looks really simple. When you have to start worrying about what the standard has to do and what the real world may want to have to deal with, it becomes a little bit more complicated. So this concatenated effect that we used here, you have to terminate that. And that was all based on going to 200 gig signaling. Now we're going to have to then go to this, worry about going into this ASIC that's based on 100 gig signaling. So now we need to use this extender. So it becomes more complicated, right? That's the reality of what the standard needs to do. We need to anticipate these sort of implementations and not just the ideal world. So getting close here to closing thoughts here at the end. There's a lot of questions where, this is very early in the process. This is just a list of the future questions that the group is tackling right now. As I've kind of highlighted, spec, both the scheme and the actual codes for each PMD is a question mark. Can we come up with a single code for everything? Maybe, maybe not. Can we reuse? Hopefully. Direct detect optics versus coherent optics at 800 gig for 10 kilometers. That is a huge point of contention. I think that's actually going to be one of the real debates that happens. All of the other stuff is kind of just cranking the switch and getting agreement, but this is a real fundamental technology choice that we have to make. I've talked about how there has been no input so far for co-packaged optics, near-packaged optics, electrical interfaces. So is that going to happen? From an overall project perspective, electrically, I look at this, I call it solving the interconnect dilemma. The people who build the channels want to know what a 200 gig channel needs to look like from a performance perspective. While the SerDes people who develop the signaling and the optical people, they want to know what does it take to make that channel work, right? So we got to deal with all that stuff. In addition, we're also seeing that people are starting to say, well, maybe we need more than passive cables because the passive cable reach isn't that long, 1 to 2 meters. I forget what the objective is at this point. Maybe we can do further if we go active. So that's another point of debate that we're starting to have. In addition, the future of 802.3df is kind of, I don't want to say up in the air at this point, but there is some, I've pointed out the trends. We're making a lot of progress at this point based on 8x100. Not as much progress with the 200 gig stuff. So we're actually talking about dividing the 802.3df project into two projects. So we would modify the DF project to only focus in on the 400 and 800 gig objectives based on the 100 gig lanes. And then what we would proposing to create is the DJ project, which would use 200 gig signaling for all of the PMDs for 200, 400, 800, and 1.6. All right. You can see here by the projected schedules that we've looked at that the 100 gig stuff will happen much sooner than the 200 gig stuff. There's about an 18-month difference right there. And frankly, there's the potential that DJ could split again in the future as well, depending on what happens with electrical signaling, optical signaling, coherent signaling development. So there's a lot of things that people are going to have to monitor, and DF today may change in the near future. All of this information that is, I've touched on is all available. Anybody can go there to get to it. I've listed the homepage. If you want to sign up for the reflectors, we do have multiple reflectors on this group. The task force reflector is listed there. And then we have reflectors addressing the logic of the project, the optical solutions, and the electrical stuff. The current project documentation is also downloadable right there. It lists what's called the project authorization and the CSD, which justifies the project, as well as the different objectives. And I want to thank everybody for the time. And please note, if you do have any questions, please feel free to reach out to me. You can reach me at the email address listed here, and you can follow me on LinkedIn. So Scott, at that point, I'm going to take a breather, and we can choose a question and go from there.
Awesome. Thank you, John. That was a great presentation. A lot of great detail and information in there. Before we get into the questions, you mentioned during the presentation, they should reach out if there's something they want to see as part of the standard and ways to get involved. Should they want to get involved, should they reach out to you via email or the link for the 802.3 homepage that we saw on the previous slide?
So either way, I'm always happy to help people. A lot of times I know the web page can be a little intimidating trying to figure out what they need. So please feel free to reach out to me. I'll be happy to help you get set up. If you're familiar with it, you can just go to the Reflector information page and sign up there. The home page for the task force does list, you can find where the different meetings are and such. To be honest, it's probably easier if people just contact me, and I'll be happy to help them. It just seems like that tends to be a lot easier for people. I don't want anyone to be scared off and confused.
All right, excellent. All right, first question. Is there any physical limit to prevent the data rate of Ethernet from growing beyond?
Wow, good question. So really when we talk about the data rate of Ethernet, that's different than the lane signaling rate, okay? And therefore, it's really a combination of how fast can I go and how wide can I go. So we're going to go to 200 gig signaling. I think a lot of people see 200 gig signaling as having real physical challenges. And what we know today as the standard front panel channel, where you have a big chip talking to potentially a retimer or directly to the module, that may change. That may move to flyover cables. It may move to near package optics or co-packaged optics. So I don't know if I don't think I would say that Ethernet rates are going to slow down, but the problems that they addressed may change to reflect the physical nature of the problem.
All right. Next question from Caroline. In a couple slides earlier, it says the condition to maximize speed seems to imply that data traffic can now be load balanced through a single channel in multiple lanes at the same time, arriving accurately at their destination. Initially, it seemed impermissible, right?
Okay, so I think there may be some misunderstanding here, slight misunderstanding. I apologize for that. It's kind of challenging. I think one of the first questions that someone asked me when I became a chair was, when will we have native 100 gig Ethernet? And I had no clue at that time what they meant. What's native? And they're like, oh, well, I mean, a single lane, a serial solution. I'm like, there's nothing in the Ethernet specification that says it has to be a single lane solution. I mean, you want an example, look at the most successful Ethernet project to date, which I would argue is the 1000 base T. That's done over 4 pairs. So the cables that we use, the category 5 cables, there's 4 differential pair in there, and the Ethernet PHY divides the data over those 4 lanes and does it. We do the same thing optically with WDM lambdas. Now, I think the question Carolyn, I'm interpreting what you're asking here based on this chart right here. And what is really going on here is that people are using the parallel lanes that is available to them in different ways, okay? And that becomes an implementation choice. The standard doesn't specify how you do what I'm showing here. What we do is we provide a solution for 200 gig over single lane. We provide a solution for 400 gig over 2 lanes, 800 gig over 4 lanes, 1.6 over 8 lanes. Okay, that's what this spec is. This chart is referring to, and the individual specifications say how to do it over 1 lane or 2 lanes or 4 lanes or 8 lanes. So it's not really a load balancing issue. It's really more just what is the PHY? What is the nature of the PHY? Is it multiple lanes or single lane?
All right, thank you. Thank you for that. Next question from Edward. For interoperability, which one, either backward or forward, is more important from the design point of view in your group?
Wow. This is Ethernet, Edward. You know that. I know Edward. So in the case of this, we have to worry about both of them. We have to worry about both of them being able to work together. We want to provide that upgrade path. So I would come back and say that I believe they're equally important. I think some people are they favor this. I talked about the sweet spot of 4x200, and I think there's a lot of interest in that. But the reality is that there's a lot of work to do. So I think 8x100 is probably going to be around a lot longer than people anticipate. So I would argue that they're equally important to get done and get out, and to make sure that we know how to make them interoperate to the best of our ability. And I believe the architecture that we have allows that. It may not always be the, what I talked about as the ideal solution. It may be, you have to use some of those extenders and you have to terminate specs depending on the solution. So, but legacy support is a hallmark of Ethernet. So I look at both of these, both 100 or forward and backwards compatibility as a very big deal.
All right, great. This looks like the last question, so we'll see if any more come in between by the time you answer this. But Paul asks, first he says, great talk, and then he says, please explain in more detail what an active cable is.
Yeah, that's a good question, and unfortunately, I have to say it depends. It depends in the eye of the beholder, and this is one of the things that at our last meeting, we actually had a presentation given to explain the potential differences in active cable assemblies. So imagine, I talked a lot about this electrical interface, the AUIs, I referred to them. And we have two of them. We have one for chip to chip, so communications between two chips. And then we have one for chip to module. So imagine you have an AUI interface, and this is probably the simplest example of an active cable that I can think of. Imagine you have this AUI driving into this cable, okay? As long as that cable can accept that AUI and then drive an AUI signal, it can apply whatever active techniques it wants to do inside of the cable itself. And that would be outside of what 802.3 does. This is market innovation, if you will. But there are people who are suggesting different types of solutions. I'd have to look into them to get back to you on what they are. But we've seen some people suggesting like partially active, so maybe a driver just on the copper side and it's passive on the far side. Maybe some sort of amplifier, if you will, linear amplifier. So there's a host of different things that would be quote unquote active cables, and that's something that the group, if pressed, will have to address. Right now, it's once again one of those things that people have talked about, but we haven't gotten formal proposals for. The traditional Ethernet approach has been the passive cable, lowest cost solution, right? No electronics, no additional power for it. So wait and see, I guess, is what I have to say. But it's probably the easiest way to think about it is that there's no active electronics in the cable itself.
All right, great. That looks like that was our last question, so it's time to wrap up. John, thank you for being here today, and everyone for attending, and everyone who sent in those really great, fantastic questions. It was a great, quick Q&A at the end of the presentation. Just a quick programming note. The computer sci has 2 additional webinars coming up in September. The first is also from this series, which is the Standards Activities Board series, on September 14th. That will be from our Cloud Standards Working Group. That will be a panel giving you everyone an update on everything they're working on. And then on September 20th, from our Build Your Career webinar series, will be a topic on project management. You'll be able to register for all these webinars using the link you'll receive in tomorrow's email, and that will also include a link to the recording and to the slides from today's presentation. John, thank you again, and everyone, thank you for being here, and we hope you have a great rest of your day.
Thank you, Scott. Thank you, everyone.